Hi, I'm Keith Johnson from Lab M08, and for my final lab, I will be modeling the solar system. In the solar system, Fnet is equal to Fgrav because gravity is the only force that acts over such large distances here, and the force of gravity is equal to gmm over r squared, with m1 being the sun and m2 being whichever planet we're looking at. Fnet is directly towards the sun from wherever the planet is, and its velocity is perpendicular to that, allowing it to travel in a circular or elliptical orbit around this planet. To simplify things in this lab, I assumed that all the planets had circular orbits. Using the data here given to us on t-square, we know the masses and the mean distances from the sun of all the planets. We plug this data in to Python and then use it to update. If the change in momentum is equal to Fnet, or gmm over r squared, then we can update the velocity by using the change in momentum divided by the mass, and then update the position with the change in velocity, with the new velocity times the change in time. Together, this allows us to map the solar system. When we plug in all of the various planets, we can see them traveling around the center point, the sun. Not all of them are quite visible yet, because Pluto, which I do consider a planet, as well as Neptune, are off screen. However, eventually they will come around. We'll see them later though, so we'll go back to the rest. Now to see if this is an accurate model, we can set a time step to various amounts, which correspond to the times it should take to one orbit. So in here, from the planetary data, we can find out how long the orbit is in terms of Earth years, and then plug that in as our time. If we plug in 0.241 years, which is how long it takes Mercury to orbit, we see that Mercury, the white ball, the white line there, makes a complete orbit, which shows that this is inaccurate. If we plug in 1 year, both Mercury and Venus have made full orbits inside several times, and then Earth, the green orbit, has made one full revolution, showing that 1 year is accurate, so that Earth's revolution time is correct. Continuing on, we look at Jupiter, which has a revolution time of 11.9 years. This does seem that we are a little bit off up there. As you can see, there's a slight gap, but it is a very close approximation. And then finally, the only one we're going to look at is Uranus, which also has a small gap, but is a very close approximation, with 89.0 years of time as a time step. Not the time step, the time it is run for. So this is a good approximation, and I went through for all the planets, and it lined up very well. As we actually here, we can see the paths of Neptune and Pluto, and showing that this was a good model, and that the physics did work, given only the masses and the initial velocities of the planets. For fun, we threw in a what-if question. What if gravity was stronger? To simulate this, we changed the gravitational constant from 6.74 times e to the negative 11th to the negative 10th, and run it. We see planets get shot off and have very different orbits. Because their starting velocities are so different, many of them assume elliptical orbits, but however closer in, there's a much more drastic change, and the planets are shot all over the place. The one that goes off here seems to be anomalous, since this is Pluto, this is Mercury, which got shot off based on the initial conditions not being quite right. Venus here will return eventually, but it just shows some interesting different paths that will be found if we had the same mass planets with the same speeds starting from a perfect line up and down, how they would react. Not that this has much application, but it's an interesting thing to look at. Thanks for watching the final lab. I hope you enjoyed it. Have a good day.